Okay, in this video we will talk about the properties of quantum Fourier transform. There are two main properties about this transform. But let me first state that, like any other quantum transformation, the quantum Fourier transform is as well a unitary transformation. Recall the matrix representation of the quantum Fourier transform, and if we consider the matrix representation of QFT, we can easily see that it's a symmetric matrix, but moreover it's a unitary operation. Okay, so let me first state that QFT of dimension n is a unitary transformation. I'm not going to write the proof here. The proof is in the lecture notes. So the first property that we will consider is called the convolution multiplication property. The convolution multiplication property. Now, if we have an n-dimensional quantum state, okay, so given psi from I0 to n minus 1, the amplitudes are alpha I. Of course, we assume that the state is normalized, so the summation of the square of the magnitudes of AI is equal to 1. So if we apply the quantum Fourier transform of dimension n on this state psi, then we get another n-dimensional quantum state psi prime with amplitudes beta I. But now suppose that if we shift the input vector one row down, okay, so suppose that originally the input vector is alpha 0, alpha 1, up to alpha n minus 1. But then let's shift this input vector one row down. Okay. What we get is alpha n minus 1, alpha 0, alpha 1, alpha n minus 2. Now let's apply QFT on this shifted input. It turns out the outcome will be exactly the same as earlier. So the outcome will be beta 0, beta 1, beta 2, and so on, except that it picks up a phase. So QFT applied on alpha n minus 1, alpha 0, alpha 1, alpha n minus 2 is equal to 1 times beta 0, omega times beta 1, omega 2 times beta 2, omega to the power n minus 1 times beta n minus 1. So if we shift the input vector one row down, the output distribution doesn't change, except that it picks up a phase coefficient here. And the phase coefficients introduced here, they come from the second column of the quantum Fourier transform of dimension n. because these are the phase factors, the phase coefficients, which are on the second column of QFT. Right? So if we shift the input vector one row down, then we get phase coefficients on the second column of QFT as reinforcements of the amplitudes. So the output distribution, the probability distribution doesn't change. The outcome is exactly the same as earlier. Since complex roots are of unit length, they don't change the probability outcome. Okay. So this is the convolution multiplication property. It's a very nice property that is used in Shor's algorithm. But the second property is even more critical, and it's about how it treats periodic functions. Okay, so remember that a function f is periodic if there exists some r such that f of x plus r is equal to f of x. So if r is the period of f, then no matter what x is, f of x plus r is always f of x. Now, given a periodic superposition state, a quantum state of length m, length m with period r, say, with period r, quantum Fourier transform this superposition state into another superposition of length m, except with period m over r. So the output state will be another periodic superposition, state of the same length with period m over r. So the periods are multiples of m over r. Okay. So let me give an example to a periodic state. To understand much better. Suppose, for instance, that n is equal to 10. And suppose that a is equal to 3. Okay. Now consider the periodic function, the modular arithmetic function. F of a n x equals a to the x mod n. So this function. Now when n is equal to 10 and a is equal to 3, in this case the period is equal to 4. R, the period, is equal to 4. So let's take m take m to be at least as large as n squared. Okay, and suppose that m is a power of 2. Could be, for instance, m could be equal to 128. I will explain later why we take m to be as large as n squared. Okay, I will explain this later on. But given this function f of a n x, a periodic superposition state would look something like, so we have 1 over square root m as the amplitudes, x from 0 to m minus 1, x f of a n x, and this will be equal to 1 over 128. If x is 0, then the output of the function is 1, plus 1 over 100 and square root 128 if x is equal to 1, then the output of the function is 3, plus same amplitude 2, 9. And then we have 3, 7 plus 4, 1. And then the sequence repeats. We have 1 over 100 and square root 128, 5, 3, right, up to 127, 7. So this is an example to superposition, a periodic superposition state of length m with period 4. Okay, so let's assume a special case for our purpose, for simplicity and for convenience. And let's suppose that R divides M. Okay, so M here is the dimension of the input vector, which is of size at least n squared, and n is the number of, so this is the number that we want to factor, number we want to factor. Okay, so remember that we are trying to solve the factorization problem, integer factorization problem. So given an m-dimensional vector, let's call it psi. Suppose that the amplitudes are alpha 0, alpha 1, alpha m minus 1, such that alpha I is equal to alpha j whenever I is equivalent to j mod r, the quantum Fourier transform maps this input vector to another vector, another superposition state of the same length except with period m over r. Okay. Input to alpha 0, alpha 1, alpha r minus 1. So it will map to a vector psi prime, which consists of m over r repetitions of this sequence. Okay, sequence of length r, and there are m over r many repetitions. Suppose now that there are exactly one of the r numbers of these numbers is non-zero. Okay, so if alpha j is, for instance, non-zero, then we say that if alpha j is non-zero, then we say that psi is periodic with period r and offset j. Offset. So offset, it basically gives us the first basis state with a non-zero amplitude. Okay. All right. So let me summarize again. The action of QFT. So suppose that we are given a periodic sequence, okay, and the only non-zero entries are multiples of r. So 0 has a non-zero amplitude, and then r has a non-zero amplitude. 2r has a non-zero amplitude, 3r, so on, up to m minus r, m over r minus 1 r. Each with amplitude square root of r over m, so they have equal amplitudes. Okay, so now this is of length m, so that's why we have square root r over m as the amplitude. And QFT, if we apply QFT of dimension m on this input superposition, then what we get is a superposition of the same length, a superposition state of the same length, So the dimension of the vector is preserved, except that the period is changed. Now we have non-zero amplitudes for multiples of m over r. 0, m over r. This is 2m over r, 3m over r, r minus 1, m over r. And each with amplitude 1 over square root r. Okay. If I write this as an expression, so suppose that psi is a periodic vector, alpha 0, alpha 1, alpha m minus 1. And suppose that psi has no offset, with no offset. That is to say, the only non-zero terms are alpha 0, alpha r, alpha 2r, and so on. Okay. So explicitly, if I have to write psi explicitly, this is psi will be equal to square root of r over m from j equal to 0, m over r minus 1, jr. So we have a superposition state which are with periods with period of r. So the non-zero entries are multiples of r. Okay. So then the quantum Fourier transform of psi will be equal to psi prime. Okay, and this is a periodic vector of length m, but with period m over r, with no offset. So first property is that it eliminates the offset, even if the given vector had an offset. It eliminates the offset, as we shall see shortly. And secondly, it changes the period. Each with amplitude 1 over square root r, j equals 0 up to r minus 1, and we have j times m over r as the basis states. Okay. So let me repeat this. First, given a superposition state with period r and some offset t, say, the quantum Fourier transform transforms the given vector into a superposition state with period m over r. Secondly, it eliminates the offsets. Alright, so in the next video we will look at the algorithm and I will give the circuit design of Shor's algorithm.